Okay, so tell me what happens when you have a soluble ionic compound enter water. What occurs?
So water molecules take apart the
Okay, I like that. Water molecule. Okay, and how come this happens? How come water is able to do this? Sorry? It's polar? Two reasons really. One, it's polar. And what's the other reason?
The negative, like the soluble, the solvent, the negative poles are being pulled by the water.
Yep, that's the polar portion of it. So it's polar, and then it's small. Are we okay with that? So the water is going in and sort of chiseling the ions out, cutting the ions apart. If you were to, if you wanted to cut something, what would you like the edge of the knife blade to be? Sharp? What does that mean, to be sharp though? Small. The edge of the blade is incredibly tiny, just the edge of the blade. And so the water molecules come in with their very tiny cutting tools, basically, and chop the thing apart. So the fact that it's polar and the fact that it's really small, I mean, how many things are smaller than a water molecule? It's only 3 atoms. It's 3 of the smallest atoms. 2 of them are the smallest atom. And the oxygen pulls the electrons in really closely, so the molecule itself is really small. The only things that are smaller than a water molecule are diatomics, like chlorine or bromine or hydrogen gas, nitrogen gas, just those 2 atom molecules. Everything else is going to be bigger. So it's a tiny, tiny molecule that cuts through stuff. Okay, for this next one here, we want to balance this, and we want to try to add states if we can, and circle anybody who's ionic. Do a whole bunch of stuff. Okay. Alrighty, so how do we balance this first one? What do we need?
12 carbons.
12 carbons. And 11 water molecules. Does anybody know what that molecule is, that C12H22?
What's sucrose?
Actually, no. It's really close to sucrose, but it's not quite sucrose, but it's really close. I actually can't tell you what it is. Does anybody know why I can't say what it is? How many different ways do you think there are to take 12 carbons, 22 hydrogens, and 11 oxygens and connect them up? A lot. So I wouldn't be able to say, because there are so many different versions of that particular molecule. But it's got 12 carbons in it and a bunch of hydrogens and oxygens. So 2 things. Do you think it's a solid, liquid, or gas?
Solid.
It's a big thing, so it's a solid. Okay, so we'll give that guy a solid. The carbon, what do you think about that? Right off the periodic table, right? This is carbon. So solid. And then the water, we'll just say it's a liquid. Anybody up there ionic? Nope. No polyatomic ions, no metals. Good to go. All right, how about the next one? What do we need to do to balance?
2 CO2s.
Put a 2 in front of the CO2, that balances out the carbons. I put a 3 in front of the water, it balances out the hydrogens. And then I've got 7 oxygens on the right side. And so if I put a 3 in front of the oxygen here, I'll have 7 oxygens on the left side. Okay. How about states? What do you think?
Solid. Gas, liquid.
What's the solid?
Not a solid. Why did you think the first one was a solid?
I looked it up, it said it was a barium chloride. It seemed like
You're on the wrong one.
which one?
The second one. Yeah, the next one, yeah, you're right. The barium chloride is a solid. I'm asking about the C2H, H6O.
Oh.
There's only 2 carbons, so that's a gas.
That would be a gas if it was just carbons and hydrogens, but there's an oxygen there, and that changes everything. This is acetone. And where do you find acetone? Fingernail polish remover. So this guy's a liquid. I'm totally not expecting you to get this yet, but we've got like a month-ish. The oxygens, gas, liquid, gas, doesn't really matter which one you pick there. All right, so the next one, what are we doing for the balancing? I think we just need a 2 right there.
2 NaCl.
Yeah, 2 ammonium chlorides, that's it. Something that might speed things up for you when you're balancing is if you have a polyatomic ion on one side of the arrow, so I've got 2 of them here, and I've got that same polyatomic ion on the other side, you don't have to worry about balancing the N's and H's individually. You can balance the ammonium ion. So how many of them are here? 2 NH4s. Well, there's 1 NH4 there, so if I put a 2, now there's 2 NH4s. And I've got 1 carbonate, and then there's 1 carbonate there, so they're balanced out. Yeah, you can go down to the atom for sure, but you don't need to. A lot of the times, just balancing out the polyatomic ions themselves makes everything happen faster. States? What kind of compounds are each of these? They're all ionic compounds, right? So they're all salts, they're all solids. And I go ahead and circle each one of these guys. And we had no ionics in the last question either. Oh, there it is. Alrighty, balancing out the next one. Looks like the aluminums are already balanced, so are the sodiums. The hydrogens are not, so I see 4 hydrogens on the left, and if I put a 2 in front of the water molecule, then I have 4 hydrogens on the right, and then the oxygens. Looks like 3, 4 there. I'm done. All right, that one was easy too. States, the first one?
Solid.
Solid? That's an ionic compound, right? So we'll go ahead and circle that one. The next one? Solid, and then we'll circle that one. And the next one? It's another salt, right? So we'll call it a solid, and then the last one, liquid. You guys don't know what that NaAlO2 is. It's sodium aluminite, and the AlO2, remember that big old list of polyatomic ions? And I said that was a tiny list, actually. Well, the AlO2 is another polyatomic ion, and there's a series of those guys, actually many of them. Alrighty, so next one here. Looks like I'm gonna need 3 irons on the left side. And I've got this phosphate here. There's 2 of them here. I bet if I throw a 2 in front of this other one, it'll make this go faster. So now I've balanced out my irons and balanced out my phosphates.
Yes.
And so I've got 6 sodiums and 6 chlorines. All right, so if I throw a 6 in front of the NaCl, I should be finished.
But then aren't the NAs, oh no.
So salt, solid, salt, solid, salt, solid, definitely a salt, solid. So get all these guys circled up. Okay, next one. Balance that guy out. What do we need? Odd number, so I must need a 2 here. And a 2 here. And a 2 there? No, that can't be right.
Just O2.
Oh, there's 4 there. Yeah, that's it. 6 right there. Just a 2 and a 2. This guy's a salt, so he's a solid, and this guy's a salt, so he's a solid, and that's oxygen, so that's a gas. I'm gonna circle that one, and I'm gonna circle that one. Okay. And alrighty, so iron, 2 iron, so I'll put a 2 over here. And then what? No, that's probably not gonna work for me. Oh, maybe. So then I put a 3 there. Why did I put a 3 in front of this potassium sulfate?
Balance the sulfates.
Because there's 3 sulfates there. So now the sulfates are balanced and the irons are balanced, and then everything else probably went along with that. So it looks like I've got 6 potassiums on the right and 6 OHs on the right, 6 hydroxides, right? So if I throw a 6 in front of here, that fixes everything for me. So salt, solid, salt, solid, salt, solid, salt, solid. So everybody here gets circled as well. Okay, C7. So I put a 7 in front of the carbon dioxide. I put a 3 in front of the water molecule, and the C's and O's are balanced. That's probably going to be bad. Looks like I can't get the oxygens to balance themselves out, so I'll put a 2 here. And so then I'll put a 14 here, and then I'll put a 6 here. Okay, so now on the right side, I've got 28 and 6, so I've got 34 oxygens on the right. And on the left-hand side,
4, 70,
I have
15
6.
molecules.
Don't I have 6?
Yeah.
There's 4 in the CHO2, so we need 15.
Yeah, so yeah, we'll need 15 more here. Okay. And what are your guesses on this guy? Solid, liquid, gas? Definitely not a gas. I would guess solid. I don't actually know what it is. But it's got 7 carbons in it and a couple of oxygens, so my guess is it's probably a solid.
And if they have the same number of carbons and hydrogens with them,
Doesn't mean anything in particular. No.
So how come the very first one, the C12H22O11, is solid and, because it has a lot of oxygen, is that why?
Yep.
Okay, so.
And a lot of carbons.
Oh, okay.
Both. Then obviously a gas, and a gas, and a liquid. All right, how about these last ones here? Well, we can't just balance the sulfate because it disappears on the other side. Hmm. Huh.
There's 2 iodides, so we make 2 HI. I think that balances it.
1, 2, 3, 4. 1, 2, 3, 4. 1, 1.
I thought it made 8.
2.
Oxygens. We have 4 oxygen.
Yeah, I think it's.
Yeah.
So those 2, so if I put an 8 there, then the H's get balanced that way, and then I can mess around with this guy and put whatever number I want. Put a 4 there. All right, that looks good. Okay, states. What do you think? We talked about this last time. What's that first substance? Sulfuric acid, yeah. So your 2 options are going to be aqueous or a gas. So it's almost always going to be aqueous. And the next one, it's hydroiodic acid, right? So another one that's aqueous. How about H2S? We talked about this. I don't actually remember when we talked about this, but it was a while ago. Is it a big molecule? No. It kind of looks like a water molecule, right? The S and the O are in the same table, so it could be a liquid, except the sulfur isn't as strong as the oxygen, so the polarness of it isn't that big a deal. This is the smell, the rotten egg smell. So it's a rotten egg smell, right? So it's a gas, yeah. And iodine, you can just look that up on the table, that's a solid. And then we'll just write down liquid for water. And nobody up here is ionic. So no circles.